The last major type of derivative that we need to know how to take is how to take the derivative of an exponential or a logarithmic function. And as we're going to find out, some types of exponential and logarithmic functions are really easy, and some take a little bit more work. Not a lot. It's not going to be nearly as bad as the chain rule that we saw yesterday. So today, looking at the derivatives of exponential and logarithmic functions, the first one we're looking at is going to be the exponential. And the first type of exponential function we're going to look at is y equals e to the x. This is my favorite derivative of all because the derivative of e to the x is simply e to the x. Pretty simple. So to make these a little more interesting, we're going to combine these with a little bit of chain rules. So we'll have something like y equals e to the 3x that we want to take the derivative of. Well, we can take the derivative of this thinking about the 3x as the guts of the problem. So we've got e to some guts, and we know the derivative of that is e to the guts, e to the 3x. We just have to multiply by the derivative of the guts. And the derivative of 3x we know is 3. So just to clean it up a little bit, we will say that y prime is equal to 3e to the 3x. It's a real simple derivative. The derivative of e to the x is e to the x. Almost too easy. We'll need to do something a little more interesting. How about y equals 7e to the 2x squared plus 5x. Again, we've got all this guts in the exponent, so we'll treat that as the variable we're looking for. And 7e to the guts, the derivative of that is 7e to the guts, 2x squared plus 5x. We just have to multiply by the derivative of those guts. Well, the derivative of 2x squared plus 5x, bring the 2 out front, we've got 4x to the first plus 5. And we'll probably leave it like that. No use in doing all the distributing, so there is our derivative. How about this one? Y equals e to the x squared minus 3x times the square root of 2x plus 1. As we dissect this one, we see an e to the guts. We also see the square root of some guts. Essentially what we have here is a product with the e to the stuff and the square root of the stuff. And again, we should be getting really good at recognizing square root. We're going to think about that as 1/2 power so that we can use our exponent property on it. So since we have a product, we're going to use the product rule. Y prime is equal to the derivative of the first times the second plus the derivative of the second times the first. So the derivative of the first, e to the guts, is e to the guts. Then we have to multiply by the derivative of the guts. The derivative of x squared minus 3x is 2x minus 3. Times the second, which is the square root of 2x plus 1. Derivative of the first times the second plus the derivative of the second times the first. Well, the derivative of the second is the square root of the guts, or 1/2 times the guts. Oops. 1/2 times the guts, which is the 2x plus 1, to the 1 less power, negative 1/2 power, times the derivative of the guts, and the derivative of the guts is 2 times the first, e to the x squared minus 3x. So product rule, power rule, exponential rule, chain rule, All of that mixed in to the same problem. Not much we can simplify in the first part, but the second part we can divide out a 2 with the denominator, so let's go ahead and do that. So for our final answer, we're going to say e to the x squared minus 3x times 2x minus 3 times the square root of 2x plus 1 plus 2x plus 1 to the negative 1/2 e to the x squared minus 3x. We can even combine this idea into a quotient rule. Let's do f of x equals 500 over, we'll say 500x, over 1 minus 10 e to the negative 0.2x. Since we have a quotient, we could rewrite this as a product, but we've already done a product rule problem. So, as a quotient, low d high minus high d low, square the bottom, and away we go. The low is 1 minus 10 e to the negative 0.2x. D high, the derivative of the top, is 500. Minus high d low, the high is 500x, times the derivative of the low part. Well, the low part, you'll notice we have e to some guts. So, well, the derivative of 1 is 0. That's boring. The 10, this is negative 10 e to the guts, negative 0.2x, times the derivative of the guts. And the derivative of negative 0.2x is negative 0.2. Low, d high, minus high, d low. We got to square the bottom. 1 minus 10 e to the negative 0.2x squared, and away we go. Don't want to do too much simplifying. We will multiply, though, to clean this up here. So we've got y prime equals 1 minus 10 e to the negative 0.2x times 500 minus 500x times negative 10 times negative 0.2 is 2 e to the negative 0.2x all over 1 minus 10 e to the negative 0.2x squared. And I guess I might even be tempted to multiply the 500 times 2 just to clean it up just a little bit more. 1 minus 10 e to the negative 0.2x times 500 minus 1,000. 500 times 2 is 1,000. X e to the negative 0.2x all over 1 minus 10 e to the negative 0.2x squared. So there we go. With the quotient rule, we have our solution. So that's the basic exponential function. The derivative of e to the x is e to the x. Pretty simple to remember. What if it's not e to the x? What if y equals a to the x? Well, then we have to tweak it a little bit. It's not just a to the x. dy dx, the derivative, is equal to the natural log of a times a to the x. The natural log of the base times a to the x. So if we've got y equals 5 to the t power, dy dx is equal to, we take the natural log of the base times the power, 5 to the t. Keep track of the variable. So it's dy dt, actually. So the natural log of the base times 5 to the t. And we can combine this with all sorts of other problems. So we could see y is equal to 7 times 10 to the 1 over t squared. And the derivative there, dy dt, is equal to 7's a constant, and we'll call the 1 over t squared the guts. So 7's the constant. Then we take the natural log of the base, the natural log of 10, times the exponential, 10 to the 1 over t squared. Then we have to multiply by the derivative of the guts. Remember, 1 over t squared, that's t to the negative 2. So we've got negative 2t to the negative 3, bringing the exponent out front and dropping the exponent down 1. The only thing we can clean up is multiplying the constants, 7 times negative 2, so dy dt is going to be equal to negative 14 natural log of 10 times 10 to the 1 over t squared times t to the negative 3. And we've got our derivative. So that's how we take the derivative of exponential functions. We take the natural log of the base times the exponential function itself, a to the t. It just so happens with e to the x, the natural log part goes to 1, and so the derivative of e to the x is just e to the x. So the other part of our discussion then has to look at the logarithmic functions. And again, it's going to be easiest when the base is e. So if we have y equals the natural log of x, turns out that the derivative dy dx is equal to simply 1 over x. The derivative of the natural log is 1 over x. So, let's take a look at f of x is equal to the natural log of 7x. This one's interesting, because if we take the derivative with respect to x of f of x, you think about that 7x as the guts. So we've got the natural log of the guts. Well, the derivative of the natural log is 1 over the guts. Then we have to multiply by the derivative of the guts. Well, the derivative of 7x is just 7, which creates an interesting situation of reducing because the 7's come out. And we're just left with 1 over x. So natural log of 7x has the same derivative as the regular natural log. Kind of an interesting consequence. How about this one? Let's say g of x is equal to the natural log of 2x cubed plus 5x squared minus 3x plus 1. Well, again, you'll notice we have some guts. All this stuff inside the natural log. The derivative with respect to x of g of x, then, is equal to 1 over the guts. 1 over 2x cubed plus 5x squared minus 3x plus 1, as long as we multiply by the derivative of the guts. And the derivative of that polynomial, bringing the exponents out front, we've got 6x squared plus 10x, bring the 2 out front, if it'll erase. There we go. Bring the 2 out front, becomes 10x minus 3. And just to clean it up, since that's all over 1, we're just going to make that equal to 6x squared plus 10x minus 3, over 2x cubed plus 5x squared minus 3x plus 1. And this is our derivative of that ugly natural log. Let's try another problem. C. H of x is equal to 7x natural log of x squared. Again, we will see that we've got some guts. We also see that we've got a product, 7x times the natural log. So we're going to have to use our product rule here, h prime of x. Whoops. We're going to have to use our product rule here, h prime of x is equal to the derivative of the first, which is 7, times the second, natural log of x squared, plus the derivative of the second. The derivative of the natural log is 1 over the guts, 1 over x squared, times the derivative of the guts, which is 2x, times the second, times the first, which is 7x. Let's clean it up a little bit. You might remember that x squared inside of parentheses can come out front. So we've got h prime of x equals 14 natural log of x plus, now this is interesting, we've got x times x dividing out an x squared. All that we're left with is 2 times 7, which is 14. So 14 natural log of x plus 14. Here's another way we could have done that same problem, though. Let's do that same problem. H of x equals 7x natural log of x squared. Let's say we didn't want to do the composition, the chain rule. Remember, if we see an exponent inside a natural log, that exponent can move out front. So really, the main function h of x is 7 times 2, 14x natural log of x. Let's see how that changes things. Now we'll still look at it as a product, 14x times the natural log of x. It's just going to be a little bit easier to take the derivative of the parts. Now h prime of x is equal to the derivative of the first, 14, times the second, natural log of x, plus the derivative of the second, 1 over x, times the first, which is 14x. Again, we'll see the x is dividing out, and we're just left with 14 natural log of x plus 14, and we get the same exact answer. So this is another case where sometimes if we take the time to notice the shape of the problem beforehand and we tweak it with our algebra a bit, the problem becomes a little bit easier. So there we go. The derivative of the natural log of x is 1 over x. The other derivative we need, though, is what if the base is not base e? What if y is equal to log base a of x? Well, in that case, our derivative of y prime, it's still going to be 1 over x, but we're also going to need to multiply by the natural log of the base again. 1 over the natural log of the base times x. So let's look at some problems where we have to do that. Let's first start simple with y equals log base 5 of x. So really strictly using the definition, the derivative is going to be 1 over the natural log of the base, which is 5, times x. And we have our solution. So let's make them a little bit more interesting. Let's do the log base 3 of our polynomial, 2x cubed minus 5x squared plus 7. Can we take the derivative of that? Well, actually I should have a y equals in front, shouldn't I? Y prime is equal to 1 over, notice first the shape, should have started there. The shape of this is we have guts. It's log base 3 of some guts. So the way we do the derivative of log base 3 is we take the natural log of the base times the guts, 2x cubed minus 5x squared plus 7. We want to show it's the entire guts multiplied, so we put it in parentheses. Then we need to make sure we remember to multiply by the derivative of the guts. The derivative of the guts, bringing the exponents out front, subtracting 1 from them, we get 6x squared minus 10x. And since this is all a fraction, we'll write them as y prime equals 6x squared minus 10x over the denominator, which is the natural log of 3, times 2x cubed minus 5x squared plus 7. And we've got our solution. One more derivative. Let's do y equals log base 2 of x to the 1/2 plus 1 all over x minus 2. We could make this into a product, or we could do this as a quotient. It's about the same either way. Let's do it as a quotient rule. Let's do y prime equals low d high, so low is x minus 2. D high, we need to think about the x to the 1/2 plus 1 is the guts. So log base 2 is 1 over the natural log of 2, the natural log of the base, times the guts, x to the 1/2 plus 1, times the derivative of the guts. And the guts, we bring the 1/2 out front, x to the negative 1/2, low d high, minus high, log base 2 of x to the 1/2 plus 1, d low, the derivative of the denominator, the derivative of x is 1, all over the low squared, x minus 2 squared. See, a little bit of cleanup. The negative 1/2 is going to stick the x in the denominator. So we've got y battery didn't just die, did it? No. So we've got y prime is equal to, we've got the x minus 2 in the numerator, all over the natural log of 2 times x to the 1/2 plus 1 times 2 times x to the 1/2, all in the denominator, minus the log of x to the 1/2 plus 1, all over the denominator, x minus 2 squared. We could take care of that compound fraction, but we're going to be content here for today. So logarithmic functions, the derivative of a log is 1 over the natural log of the base times x. Turns out when you have a base e, the natural log of e goes away, and so the natural log comes out as just 1 over x. So as we kind of wrap up this unit, we do have one lesson left, but there's not really anything new in terms of derivatives in the last lesson. We're just going to do the exact same thing we've been doing with lots of variables. But today wraps up our formulas. So let's do a review of the major derivative formulas. You should have all of these memorized. You should know all of these. We've done 11, and a lot of them are almost second nature now. You don't even need to study them. If we take the derivative of a constant, the derivative of 7, you should know the derivative of a constant is 0. If we take the derivative of some x to the n, you should know that derivative. We pull the exponent out front, and then it's x to the n minus 1. We subtract 1. You should know that the derivative of a constant times a function, if there's a number out in front, we can kind of keep that constant and then just take the derivative of the function. Another one that should be familiar is if we want to take the derivative of f of x plus or minus g of x, adding or subtracting functions, we can just take the derivative of each function separately. We should know our product rule. The product rule says if we take the derivative of two functions that are multiplied together, we take the derivative of the first times the second plus the derivative of the second times the first. And try and get these all on one screen. We'll see how well I do. You should know the quotient rule. The derivative of f of x divided by g of x. The quotient rule is going to be low d high minus high d low, and then we square the bottom, and away we go. You should know that the chain rule, if we've got a function with another function inside it, we've got some guts, so to speak. You should know we take the derivative of the function with the guts times the derivative of the guts. Then today we took the derivative of e to the x. That one's easy. That's just e to the x. And we took the derivative of a to the x, or some other base. And that was essentially the same. We just first have to take the natural log of the base times the exponential function. Then we took the derivative of the natural log of x, which is the reciprocal of x, 1 over x. And finally, we took the derivative of log base a of x, which is 1 over the natural log of the base times x. Got them all on one screen. We've got 11 formulas here that we've seen. You should know all of these if you don't know them already for the test. Now granted, you should also know how we find derivatives based on the definition, where the limit as the limit as h goes to 0 of f of x plus h minus f of x all over h. We'll use the definition a bit, but we're going to use these derivative formulas a lot. You should be very familiar with them. You want to have them memorized even before tomorrow, our last lesson in this unit on derivatives. Take a look at the homework. Get it as much as you can completed. Come to class with questions, and we will see you tomorrow.